Alright, this is just providing some extra details as well as a brief research update about some research on QLCS Mesovortices that myself and a team of a bunch of other researchers and forecasters have been working on. Really, we're just building on some great research that's already out there, namely the 3 ingredients method, which is environmental and radar-based guidance to help forecasters anticipate when and where a mesovortex might develop. Now, despite this really good research, it's still a forecast challenge to try to determine where a mesovortex is going to develop and how strong it might be. So what we want to do is just figure out whether some dual-pol signatures might be helpful, especially when incorporated into the 3 ingredients method. So far we've analyzed KDP cores, KDP drops, and ZDR columns for our dual-pol signatures. We've also looked at -20C reflectivity cores and what we're calling a low-level area of enhanced spectrum width for the single polarization signatures. So far we've looked at 113 mesovortices, with 76 of those being tornadic and 37 of those being non-tornadic. And really our goal is just to potentially provide a supplement to the 3 ingredients method framework. So just jumping right into the results, we found that mid-level KDP cores and low-level KDP drops do precede a lot of the mesovortices that we're looking at. So this animation is showing an example of a KDP core, which is at mid-levels, and it is near the environmental melting layer, so that's what we're calling a mid-level KDP core. And it's typically located either within the rear inflow jet or on the very leading edge of the rear inflow jet. And this animation shows an example of the KDP drop, which is typically on the back side of the convective line. And it's similar in theory to the reflectivity drop. So basically you have a descending rear inflow jet. With that you get evaporation. And so as you lose those raindrops, your KDP and your Z decrease. This particular animation also shows another signature, what we're calling a low-level KDP core. So just a KDP core seen at the 0.5 degree elevation angle. We'll talk more about that signature a little bit later, but just wanted to point it out in this animation as well. With the KDP drop, we have seen that there seems to be a preferred location for a mesovortex to develop relative to that KDP drop. So I've placed a line on the KDP drop here, basically dividing it in half. So here's the KDP drop, basically left side from a storm relative sense and right side from a storm relative sense. And when we look at all the mesovortices, we see that the preferred development location is on the left side of that KDP drop, with nearly 80% of tornadic mesovortices forming on the left. Now, it's not always the case. We do have some mesovortices that are forming on the right, but with that preferred location in mind, that could help forecasters anticipate where a mesovortex might develop when they see that KDP drop. And this is a good time to point out that almost all of the mesovortices that we saw so far were preceded by a KDP drop, so over 90% for both tornadic and non-tornadic mesovortices. And whether it's low-level or mid-level KDP cores, we generally see that they're stronger with tornadic mesovortices. So on the left is that low-level KDP core. We're at 0.5 degree elevation angle. And you can see there's a pretty good separation between the distribution of tornadic and non-tornadic mesovortices. The N is the sample size. We've got 26 non-tornadic mesovortices with a KDP core and 61 tornadic mesovortices with a low-level KDP core. And then the statistical significance is seen here with the p-value. So same idea on the right, but this is the mid-level KDP core, or the one near the melting layer. And once again, we can see a good separation between the distributions of tornadic and non-tornadic mesovortices. And similarly, we see that the low-level and mid-level KDP cores are generally stronger with stronger tornadoes. Now, when we grouped EF0 and EF1 together, and EF2 and EF3 together, we didn't see a statistically significant difference between the two. But you can imagine that if we were going to compare maybe EF1 and stronger tornadoes compared to the non-tornadic, which is shown by the NA down here, we might have even stronger statistically significant differences than when we look at EF0 and stronger tornadoes altogether, like was shown on the previous graph. So one of the single pole signatures we looked at was low-level area of enhanced spectrum width, which you can see developing here in this animation. They're usually co-located with the mesovortices, which we would expect, and we see them a lot with tornadic mesovortices as well as non-tornadic mesovortices. Now this particular example, the non-tornadic mesovortice doesn't have a super clear low-level area of enhanced spectrum width, but other non-tornadic mesovortices that we've observed certainly have had that. With this spectrum width, it is generally higher for the tornadic mesovortices. You can see in this violin plot again, good separation between the distributions. We've got statistical significance going on. But one caveat is that this signature doesn't tend to develop prior to mesovortices. Maybe a volume scan or two, and with sales running, that might be 1 to 2 minutes before a mesovortex develops, maybe as much as 3 or 4. But for the most part, the spectrum width signature develops at the same time as the mesovortex. So not really a precursor signature, whereas the KDP cores that I was talking about earlier, those do precede mesovortex development. With ZDR columns, we've looked at those, and it doesn't appear as if that signature is going to give a lot of information. So showing violin plots here with tornadic and non-tornadic mesovortices, we see that there's really not much separation between the distributions. Now it does precede mesovortex development, but will you be able to say much about the character of that mesovortex? Maybe not. And also there are lots of ZDR columns and updrafts along a QLCS, so this may not be the best precursor signature. Even when we break out the ZDR columns based on range and instability, because we would expect to potentially see some influence, whether it's range from radar or especially from the environmental characteristics like instability or time of year, even when we separate them out like that, we don't see much differences between the tornadic and non-tornadic mesovortices. I'm showing a close or low CAPE, so below 1200 joules per kilogram, and different ranges, less than and greater than 59 kilometers. We don't see differences here, and the same is true if we look at those high CAPE environments, so CAPE greater than 1200 joules per kilogram. We'll just end off here with, I've mentioned that a lot of these signatures are associated with mesovortices, so we can see that most of the signatures you're getting 75+% mesovortices have these particular signatures, with the highest or most prevalent being that low-level area of enhanced spectrum width. We didn't talk much about those -20C reflectivity cores, and that's because they just didn't precede very many of those mesovortices, or they weren't associated with many mesovortices, less than 50%. And I think one of the reasons for this is actually with QLCS typically having a little bit lower CAPE than classic supercell environment, the reflectivity cores just weren't all that deep. So we didn't have a lot of high reflectivity at -20C. So it's possible that if you looked at a different threshold, maybe 40 dBz at -20C or maybe 50 dBz at -10C, you'd see these cores a lot more common. But with 50 dBz at -20C, we just didn't see that all that often with these QLCS mesovortices. So just to summarize all of this, one big disclaimer is none of this is peer-reviewed yet, so if you have any comments or criticisms, always feel free to reach out. And this work is still ongoing. We've got more cases to analyze. I don't think the results are going to change a lot in a big picture sense, but we are still adding cases to this particular data set so far. So from these 113 mesovortices, we see that KDP drops and mid-level KDP cores could be a good precursor to mesovortex development. They were typically observed before a mesovortex developed. And then KDP cores, whether it's low-level or mid-level, could provide some information about the mesovortex tornado potential. The low-level area of enhanced spectrum width could be a good diagnostic signature because we see it with a lot of mesovortices. There are some differences between the tornadic and non-tornadic mesovortices in terms of the magnitude of the spectrum width, but it doesn't really develop before the mesovortex develops. So not necessarily predictive, but maybe diagnostic. And then the ZDR column and -20C reflectivity cores might not provide a lot of useful information. So thank you, and feel free to reach out with any questions.